So design review next week. Is everybody ready? All of your projects work and ready for delivery?
Perfect.
Yeah? Excellent. I know yours doesn't. Okay, so does everybody have 4 or 9 lecture credits now, depending on how many you needed? Is this the last one? Anybody need more than one? No? Okay. All right, well, this is the last one for you then. So you guys are all just here because it's your last one you need, not because you care about testing, right? No? Anybody like testing? Yes. Okay, well, maybe. Maybe a few of you will be test engineers in a year or two and you'll change your mind. Hi. 1A. Sure. So we're going to talk about project testing or product testing today. And you can see I've got a big V and V on the board. That's intentional. So there are 2 major phases of testing: verification, validation. We'll talk to an annoying level today about what the difference between those is, because it's something that people screw up very commonly. And try and explain to you how you figure out what tests you should run on your project. And then a little bit about how to set up test protocols. We won't talk a lot about like how to execute specific tests, because you all come from different fields, different backgrounds, different kinds of projects. There are too many. I don't know them all. So it would be specific to your test, but I'll help you figure out how to get there, how to figure out what you should be doing. So again, today we'll talk about verification and validation, and a lot about what those mean, what the difference between them is, about how to do a test, and then a little bit about how to write your reports. They're pretty simple if you do them the easy way, okay? So the first thing, verification, validation. So the kind of classical, are you laughing because you've heard this a million times or what? No? Okay. The kind of classical definition of these, or kind of catchphrase, try to say these are, verification is, did we make it right? Like, so we made some product, did we make it right? And validation is, did we make the right thing? Okay. So you can think of those like, we set out, we had this concept and we made this thing. Did we make it the way we intended? Is verification. Validation is, did we make it the way that our user needed it to be in the first place? Okay? Does everybody see the difference between those? There are very different types of testing that follow from those 2 things. Your verification tests will map back to your specifications. So when we talked about the design process, first we did user needs. Those were those broad functions of the project. And then we did specifications where we got more detailed, more specific, and we became quantitative, right? So your verification test to your specifications, your validation test to your user needs. So if we said, I'm building a skyscraper, it should be able to withstand 50-mile-an-hour winds. I can apply 50-mile-an-hour winds. That's a verification test, okay? Say I do a simulation of that. That's a verification test. So you had some quantitative measure, and you blew wind across it, and that was what you tested. Now your validation test might be, I build a skyscraper. It's supposed to house certain number of people. There should be a certain number of office buildings. It should be able to get, custodian from one floor to the next. Those are validation tests. Okay, so you're going to say, did it not did it meet my requirements, but did it do what it was supposed to do in general? Okay, so those are kind of the differences. So I'll look at that again, a little bit different way. You should say, my user need would be my product should do something, and my validation test is it can do that thing. Right, that's the outcome I'm looking for. So if we say that, right, we say my car should be able to transport 5 passengers, I could say that, in my specifications, it should be at least a certain number of internal cubic feet of volume, right? And that's what I correspond to 5 passengers or 7 passengers. But I didn't actually put people in there in that verification test, right? When I get to my validation test, I would actually put people or simulate, put dummies, something like that, in that car and find out, can they actually fit in there? What are the things you didn't think about in that case, right? So there are plenty of times when you can meet your verification test and then fail your validation. Right? Verification tests usually come first. Right? So if you think about, I've created something with some beam and I'm going to apply a load, like a lot of you have done in your materials classes, those are verification tests. Right? So you're looking to say, I did this quantitative assumption as to what this thing would be, right? I made some beam or some member with a certain thickness out of a certain material because it would be able to withstand this load. My verification test would be, I actually apply that load and see if it if it actually meets that, right? So if the real world application meets my design, my theoretical one, and then my validation would be actually using it for its intended purpose, right? So those of you who are in software, things like that, when you get into alpha testing, beta testing, those are validations. You're actually putting it out in front of someone and using it. Where your unit tests or a function test, where you're looking at some little part of your design, those are verification tests, okay? So again, verification would be meeting your specification. Product should meet some criteria. Yes, it meets that criteria. That's verification. This thing still doesn't like me in this room. So one way to kind of look at that, this comes from medical device industries. You'll see it says medical device, but you could substitute any kind of product in here, and we can map these things. So if you say, I have some user need, that's usually where we start in our project, right? We defined our project, we went and met with the user, we found out what it is they need this thing to do. And then as you went through the design process, you created inputs. So this is what we'd call specifications in our design process. You went through and did some conceptual design, detailed design, where we actually created some outputs, like prototypes. And then you ended up with some final product. So the mapping here would be when I get to design outputs, or what we would call the detailed design phase, those really detailed plans, we're going to go back and check them and see, verify them. Did they meet my design inputs or my specifications? So different wording, same idea, okay? And then my final product, I'm going to validate and make sure that it meets my user needs. So I'm going to go back to that earlier level. It's really hard to do validation testing without getting a real user, okay? So you typically in validation, you're saying, you came to me with this need, or I saw this need. We went through this whole process of design, and now I want to say, does this work? Does this satisfy your needs? Okay. A lot of your projects in EPICS, the validation is sort of the delivery, because you're not going to mass produce these most of the time. So whenever you bring it to your user, you say, try it out, see what you think. Okay. So say you're in one of the teams that's working with Imagination Station downtown, Children's Museum, and you build a display. Your validation may be when you have the museum director or someone from the museum come in and say, yeah, this does what we intended it to do. And then the use is whenever they put it in the museum with kids. Does that make sense? So verification activities typically happen sort of in-house engineering tests, where validation activities tend to be user-centric. Make sense? Okay. So one last way of comparing these things, and this one kind of focuses on communication. This is an old cartoon, so this is from the 1970s. But it really comes to the point of validation. So say this is as marketing requested, this backyard swing, right? So your marketing people, so in your case, maybe the team 4 semesters ago who talked with the project partner had this concept of what your design should be. Okay, so you as the person designing it this semester maybe never talked to them about it. As sales ordered it, so again, a communication thing, right? So who was it that talked with the user? Is some other, ridiculous thing? As engineering designed it, so most of us in the room are engineers, and we tend to screw these things up, right? So we misunderstood along the way. And you could say as we manufactured it, as field service installed it, it's my favorite, very practical. And then what the customer actually wanted was something very simple, right? So the communication as you go along the way. So you can maybe have these designs in all of these cases and verify them and go back and say, okay, this swing right here needed to hold 400 pounds, it needed to hold a person on it. You could do all of those verification tests and fail your validation because it's not what the user really wanted, right? That looks like an uncomfortable swing, especially for the fellows, right? So, so you could come up short on what you did even by following through the design process. So it can fail you if you neglect to do your verification validation testing. Likewise, if you don't do your verification testing, you could put a person on this swing right here who's particularly lightweight and small, and they could swing and you could say, look, it works. But you didn't do a verification test to check the strength of this rope, and then a bigger person comes along and they fall on their butt, right? So this is why you need to do both forms of testing. They're both important. Okay, so that's kind of a silly one. All right. So some types of these tests. So verification tests could be things like a unit test in a code. So those of you who write software and you write functions, right? These are very obvious cases for doing verification, right? So say I write a function to multiply 2 numbers, right? I input the 2 numbers, I get an output, I check to see if it's the right output. but maybe I also need to put in some different types of numbers, right? As I'm doing verification, maybe I need to put in 0 to make sure I handle dividing by 0 or multiplying by things like that. So you can look at those weird cases, right? Did I put in negative numbers or 2 negatives? Do I get the output that I expect from that function? That's a kind of verification test. If you're a mechanical person, you could think about the classic tensile test, right? So you have some piece of material, you put it on a test rig, and you just pull it apart and you look to see how much load it can handle. So those things are kind of classic verification tests, but you could get way deeper into the weeds on your particular project to verify each piece of it, like the rope in our swing, okay? Likewise, validation testing tends to be user testing. Some other good options would be simulation. So sometimes you can't do tests. So you can't do a real test. So when we would do validation tests in medical device industry, we'd usually use cadavers. Okay, so we would go through, we'd do lots of verification tests on mechanical test equipment. Okay, so you would bend parts and you would load parts and you'd look at what's their fatigue life, things like that. When we would go to do validation, you wouldn't want me to come in and say, hey, I made this cool new medical device, can I validate it on you? Right? You probably wouldn't think that was too nifty. So we would use cadavers and we'd go into a cadaver lab and we would perform the operation on a dead person's body and make sure that everything worked the way you'd expect it to do. I got a lot of trouble with my wife one day. I was leaving in the morning on a Saturday to go into work for a cadaver lab. Sometimes we do them on the weekends. And my daughter was 2 or 3 at the time. She said, why are you going to work on Saturday? I said, oh, I'm just going to cut up some dead bodies. And my wife was like, oh, what did you say? But that was, that's a day at work. So simulated use is a normal thing. A lot of other occasions in medical devices where you might need to do that. If you have something that's very expensive and you don't want to break it intentionally, right? So say you're developing a new MRI machine and it costs $100,000. You don't want to break one of them just to see if it worked. You might do some simulation. If you're putting something into space, you might not want to try one out first, right? So there are a lot of occasions where simulated use makes more sense than doing physical testing. But a lot of the times in those simulations, you have to do a validation of your simulation, which can often be just as complicated, okay? So you may have to go back and say, I did this simulation. How do you know that that reflected real physics, right? How do you know that that reflected the real situation? So you may have to, depending on the situation, prove that your simulation was real, made sense, okay? So you might do some functional tests where you actually try something out, or you could do performance tests. So if you say, I expected this thing to have some certain level of performance, you might do it here. So you can imagine if you designed some new running shoes, you could do lots of verification tests, but your validation test is you'd want to have someone go out and run it in the kind of race it was intended for, or something like that. So those are some performance tests. Alrighty. So we're going to do an exercise just for a few minutes. Does anybody recognize this big marshmallow-looking character up here? Yeah? You guys still watch kids' movies occasionally? So this is Baymax from movie Big Hero 6, and he is a healthcare robot. Okay, so his purpose is, if you say, ouch, he springs to life, comes and tends to whatever ailment you have and won't go away until you say you're satisfied with your care. What I'd like you to do is write one user need and validation pair. So you're going to write one user need. That's one of those broad functions of what a healthcare robot would do, a real healthcare robot, and write one validation test or propose a validation test. So you don't need to write a test protocol, just write one sentence what you would do to validate it. Corresponding to that user need, write one quantitative specification and then write at least one sentence verification as to how you would verify that. I'll give you a few minutes to do that and then we'll partner up and we'll discuss those. So go ahead and start on that. guys count up with some user needs. You got a need? What's your function that you're wanting to tell? Thinking about it? So healthcare robot, you can think of it like a robotic nurse or a robotic doctor, right? So they're going to come take care of you if you're hurt or sick. So what are some of the functions that would need to do? And then how could you quantify one of those functions? How would you test those? Is this too hard or are you guys asleep? What's a robot?
And it has to be specific to Baymax?
Doesn't have to be Baymax, but a healthcare robot, right? So some kind of a automated nurse, automated doctor. Or it could be Baymax if you want. It doesn't have to fight bad guys. Or, Okay, if you haven't done so, partner up and discuss what your findings were, see if you guys kind of came up with similar things or different, and just kind of discuss if your verification tests are verification and your validation are validation. All right, okay, come back. All right, somebody want to share one of their, hey guys, calm down. Somebody want to share their user need validation pair? You guys do? Yeah, what's up? What was your user need?
One of mine was respond or recognize when someone's in pain.
Okay, recognize when someone's in pain. How'd you validate it?
Simulate an injury.
Simulate an injury, okay.
Not necessarily injure someone, but simulate one.
Okay, good plan. And what was your specification to go with that?
One of my specifications was it would be able to like lift a 180-pound man
To lift a 180-pound man, okay.
and verify it by lifting like a dummy off the ground or something.
Okay, all right, that's a good one. Lifting a dummy off the ground, that's 180 pounds, okay. Anybody else want to share? How about somebody over here? No? How about you two that keep laughing? You got one?
I had the exact same thing, but my specification was like that you gently put on a Band-Aid, so you don't let someone like whip a Band-Aid on you.
Okay, sure. Gently put on a Band-Aid.
Yeah, so you could do some type of like pressure test.
Okay, a pressure test. That's good. Okay, so does everybody kind of get those concepts, difference between the two? Sounded like it. All right, very good. Okay, so moving forward, since we all just came back from probably eating too much pie, good example, when writing your test protocols, they're a lot like writing a recipe. So I've used this example a couple times before, but it's pertinent to this. So most of you have probably made something from a recipe before, although maybe not. But typically you'll have a list of steps in a recipe that have to be followed in order, and they will be very specific, right? And they usually don't leave out any information unless it's something really commonly known, okay? So it'll tell you preheat the oven to 350 degrees, and then it'll go through each of the, like mix these set of ingredients together first, and then these set of ingredients, and then cook it for this long, and here's how to check to see if it's done. Okay, so you'll have this specific list of items. Your test protocol should go just like that, okay? So typically in your test protocol, you'll want to go through, write out a series of steps. And the protocol should be specific. So you don't want to say, check to see if it broke, okay? What does that mean exactly, right? That's not very good. So say a better option would be to say, okay, we're going to fixture this thing in this certain way, right? So say we're going to do it 3 inches from the end of a handle, and we're going to apply a load at this point. So this is a mechanical test, obviously. Apply a load at this point for this long, at this rate of loading for this many cycles. You want to be very specific and go through all of those details one by one, sort of in order, okay? So you want to do it just like you would be following a recipe. I say that's better, not good, because that's still really not nearly enough detail for a test protocol, but it would at least give you some idea what you could do. And the purpose of that is because if someone goes and they change your design 5 years from now, they want to be able to go back and rerun that test in the exact same way to find out if the changes they made have caused it to no longer meet your specifications, right? So you met with the user, you came up with all these specifications. You don't want someone later on to change your design in a way that would no longer meet those specifications. If you then go into acceptance criteria, so you've said, I want to test it until it breaks. You want to say, what exactly does that mean? And you want to spell that out before you run the test. So a common inclination is to run a test and then decide if that test passed or failed based on criteria that you didn't set beforehand, right? So you get to it and you say, yeah, I think that was good enough. You really need to set your criteria beforehand to have your test have any credibility, right? So you need to say, I'm going to run this thing for this many cycles. It needs to get this much weight without this kind of failure, and you need to set those up front. So if you say a bad acceptance criteria might be the sample passes the test if it does not break. What exactly does that mean again? A better would be to say it's accepted if you've observed no yield under a 200-pound load. Okay, so that's better. You still could get into a lot more detail than that. So specify those things up front. Never kind of create your acceptance criteria after the fact. So we kind of ran it through a test, and then we saw it could hold 800 pounds, so I said it needs to hold at least 600 pounds. Oh, well, great, right? So you picked something that it would pass. That's not actually being a valid test. Your test acceptance criteria should be based on some objective measure, right? Or at least some logic. behind them. Okay, so if you're creating that skyscraper and you say it should withstand 50-mile-an-hour winds, that 50-mile-an-hour requirement should be stated beforehand, and it should be based on some intelligence, right? So you measured wind speeds in this area, or this is the maximum wind speed that's occurred here in 20 years, or something intelligent, right? You don't want to leave it up to chance. So when you get into writing your protocols, so you kind of know you're going to write them like a recipe, but you format them much like you would format an academic paper. Okay, so if you're going to put a paper in a journal, you usually will have these ideas like backgrounds, your methods, your results. Okay, so your protocol, you'll just want to make sure that you specify what the product was and what version of it. So as you go through and change that product, so say as of a certain date or a version number, so that you know which one you were testing, the name of the test, if it's a verification or validation test, who was running the test, and then you'll include a background. Why are you doing this test? Why was this test found to be relevant? Hopefully that will be because you had a user need or specification, right? We had a user need or specification. We needed to find out if we met that user need or specification. So in light of that and why that user need or specification is important would go in the background. And then your materials, you would talk about exactly what you were testing. Were you testing 1 piece or 10 pieces? How many replicates of this did you do? Your methods are going to be that recipe, right? Here's the specific steps. And then you'll list your acceptance criteria. And that's your test protocol. They're really simple to do, but if you organize them like this, people will be able to follow them and understand what you were trying to do. Where a lot of times we'll write a test protocol sort of off the cuff without a format, and they can be really hard for other people to understand later. And then the really nice thing is when you go to do your test report, you take the exact same thing, but you change where it said protocol and you write report. You take the exact same background, materials, and methods, but you write in anything that you had to change, okay? So a lot of times you write that protocol, and then when you go to execute it, something comes up, and you can't do it exactly like that. That's okay. It's okay to change the protocol to be able to meet, say, a piece of equipment wasn't available that you intended to use, or you couldn't get enough samples. You can deviate from those things, but you want to justify them here, okay? So I had my protocol, I said this is what I was going to do, and then when I went to do it, these things changed. Here's the results of my test, right? Here's the data that I got out of the test, and my conclusions. So you can copy and paste 90% of your test report from your test protocol, right? It's really easy that way, and it makes them really easy to read, okay? So if you go through, I read your protocol, I saw your data, I understood the differences, why you did what you did. Because what you guys don't realize is when you create products, they live longer than you may work on them. And when other people go to work on them, they'll have to read your output. Even here in EPICS, right? We have projects that last semester after semester. You guys come and go, you graduate, you leave. People come in to work on those things, and it's hard to follow what you did if you don't document things really well. And this is a really easy way to let people know how you did your testing. And it's a nice formal way that will be accepted by your future bosses or regulators, people who are going to be interested in the quality or outcome of your work. Okay, so one piece to know, we tend to think in terms of testing our whole product, right? We made this product, we're going to test the whole thing. A lot of times that's unnecessary. We can do simple things to try and reduce the complexity, the costs, and the time of our tests. So before you run a test, you have to fabricate the parts you're going to test, right? You have to make the prototypes or the end-level parts that you're going to make, and that can be slow and expensive. The tests might be expensive to